Welcome to Operating Systems Unit 10, Part 2 on deadlocks, deadlock avoidance, and the banker's algorithm. So in deadlock avoidance, processes use resources and they share different instances of different resources. And processes need to indicate which resources they need, and the operating system needs to make choices on how to allocate the resources to the process and keep it in a safe state. So the simplest way is for each process to indicate the maximum number of each resource that it needs. And then the system will allocate these resources in a way that when a process finishes using that resource, it can be freed up and used by another process. So one way to do this when you have limited numbers of the resources is just to use a resource allocation graph where processes make a request for a resource and resources are allocated to processes. And in this situation, we have three processes, P1, P2, and P3, and we have four resources, resource 1, resource 2, resource 3, and resource 4. And the dots in the resources indicate how many instances there are of each resource. So as you can see, P1 is requesting resource 1, and there's only one instance of it, and it's in use by P2, which is also in using resource 2, but it's also requesting resource 3, and resource 3 has been given to process 3. But you can see that there won't be any problem here because when process 3 is finished with resource 3, it will be free, and then P2 can use resource 3, resource 1, and resource 2 and free those up, and then P1 can use resource 1. So we have a safe situation here. If P3 were to make this request, where P3 is requesting resource 2, then we have a problem because we have cycles in the graph, and when there's a cycle in the graph, then there's a chance you will have a deadlock because if P3 makes the request for resource 2, there's no way for P3 to free up resource 3 for P2, and we have a deadlock situation. So we have two cycles here, one cycle that starts at P1 and ends at P1, and a second cycle that starts at P2 and ends at P2. So when you have a cycle, then the system is not in a safe state. Now we're on to the banker's algorithm, which is a way to allocate multiple instances of resources. So if there are, in this case, we have four resources, 0, 1, 2, and 3, and there's 8 instances of resource 0, 5 instances of resource 1, 9 instances of resource 2, and 8 instances of resource 3. So the banker's algorithm, what happens is we have a couple of matrix here. We have each process, we have 5 processes, and these 5 processes are using these different resources. So what happens is the processes will indicate ahead of time the maximum they will need of each resource. So P0, for example, P0 says, indicates that it will need 3 instances of resource 0, 2 instances of 1, 1 instance of 2, and 4 instances of 3. And the operating system will allocate those resources that exist in the system amongst the different processes and make decisions on how to allocate these resources in such a way so that we will end up in a safe situation and all processes will be able to complete their work. So as you can see, the processes have not, the operating system has not allocated all of the resources out, and processes have not been allocated the maximum that they need. So to calculate that, to figure that out, you use the banker's algorithm, and the banker's algorithm has an extra matrix and it also has a vector. So this extra matrix is the need matrix. This need matrix is going to calculate those resources that have been allocated subtracted from the maximum. So for example, P0 has a maximum of resource 0 is 3 and it has been allocated 2, so it needs one more instance of resource 0. And then when it completes using that, it will be able to free up for the other processes. And what you do is you calculate the need for all of the processes for all of the resources. So P2 needs maximum of resource 1 is 2, has been allocated 0, so the need is 2. And it's just done by simple subtraction, and you can get all of the need for all of the processes. So P1 has a max of 0 and has been allocated 0, a max of 1, a max of 2 here and has been allocated 1, a max of 5 here and has been allocated 2, and a max of 3 here and has been allocated 1. P2 has 5 minus 4, 1 minus 0, 0 minus 0, 5 minus 3. P3, 1 minus 1, 4 minus 2, 3 minus 1, 0 minus 0. P4, 3 minus 2, 0 minus 0, 3 minus 3 is 0, and 3 minus 0 is 3. So now we've calculated the need, and in order to do the algorithm, what you want to do is you want to see if the available will satisfy the needs of any one process, and then what has been allocated can be freed up for the other processes. So in order to do that, we need to add up what has been allocated for each resource. So resource 0, there are 8 instances of resource 0 that have been allocated at this time, and there are 8 that exist in the system, so the available will be 0. Resource 1, we have 3 that have been allocated, and there are 5 in the system, so the available will be 2. And for R2, there are 7 that have been allocated and 9 exist, so the available will be 2. And R3, there are 6 that have been allocated and 8 exist, so the available will be 2. So you can see here we have 8. 8 minus 8 is 0. 5 minus 3 is 2. 9 minus 7 is 2. And 8 minus 6 is 2. So now once we have calculated the need and we have calculated the available, we can go ahead and do the algorithm. And to do the algorithm, all available resources must be greater than the need. So you just go through and you compare the 0, 2, 2, 2 that is available with any process. And there's no particular order. It's just that it has to satisfy the request, the need of the process. So we'll start with P0, and if we have available 0, 2, 2, 2, that does not cover the need of P0. But you can see that it does cover the need of P3. It doesn't cover P1, P2, but it does cover P3. 0, 2, 2, 2 is greater than 0, 2, 2, 0. So what will happen is P3 will be able to use the resources that are available, finish all of its work, and then those resources that have been allocated to P3 will then become available for the other processes. So this available will be put back into the pool of available. This allocated will be put back into the pool of available, will be added here. So we will take the 1, 2, 0, 1 and add it to the 0, 2, 2, 2. So our available will now change to 1, 4, 3, 2. And now we take this 1, 4, 3, 2 and we go through and we see if we can satisfy the request of another process. And you can see that there are a couple we can, so we'll just pick P0, satisfy the requests of P0, and then those that are available that were allocated to P0 will then go to available. And so the available will then change to 3, 4, 4, 4. And the way I got that was by adding the allocation, what has been allocated to P0, to the available. And then P0 is done. And now we have 3, 4, 4, 4. And if you look through, you can see that 3, 4, 4, 4 will satisfy the need of any of the leftover processes. So the available can only go up, so now we know that yes, this is a safe state, and one sequence for this to be a safe state is P3, P0, P1, P2, P4. And the important part of the sequence is that P3 must be the first one in the sequence, because when we initially calculated the available, P3 was the only process that the available could satisfy. So now let's take a quick look at the same situation, only this time R3 does not have 8 instances, it has 7 instances. So therefore, all of the need will be calculated the same, and the available will be calculated differently, because instead of having 8 instances available of R3, we only have 7. So we will have an available of 0, 2, 2, 1 instead of 0, 2, 2, 2. And this is just the example of a situation in which it is an unsafe state. So the only change I made from the last one is that I changed the number of instances that exist for R3. And so therefore, when I made this subtraction of 6 that have been allocated from the 7 that exist, it changed to a 0, 2, 2, 1. So now we can proceed through the algorithm, and we can see that P3 can be satisfied. So we will take what has been allocated to P3 and add it. So we take the 1 and add it to 0, we have 1. The 2 and add it to 2, we have 4. The 1 we added to 2 and have 3. And the 0 we added to 1 and we have 1. So now we have available 1, 4, 3, 1. So you can start just with the 1, and you can see that that's good for P0, P1, and P2. But then with the 4, that's good for P0, P1, and P2. And the 3 is also good for P0, P1, and P2. However, resource 3, there's only 1 available, and the need for all the 4 remaining processes is greater than 1, which means that this is not a safe state. And the way to fix this is the operating system would then have to go and change the allocation, because you can't change the number. I changed the number of instances for this exercise, but it's not going to change the number of instances that exist. It's not going to change the maximum that a process is going to need to fulfill its tasks, but the allocation can be modified in order to put the system into a safe state. So the answer on a question or for this exercise is that no, this is not safe. Okay, and the last part of deadlock is detecting and recovering. So in a system, you could either ignore it, prevent or avoid it, or the last thing is you could allow the system to enter a deadlock state, use an algorithm to detect that a deadlock has occurred, and then recover from it. And that concludes Unit 10, Part 2.